Good morning, class. Today we're going to talk about two-part problems. These are problems that are going to require multiple steps for us to solve. Most of the time, though, when you're looking at these problems, you're going to organize it into sequential or time-related events. So it's very important to understand when something is occurring in a problem. One of the most necessary things that you're going to have to do when solving these problems is summarizing these problems and restating them. When you restate them, though, and you use an and then sort of phrase, then that indicates a place where something is happening and then there's a change in the situation. And that gives you a natural break where you know you have to solve different situations that may just be connected through time. I'm going to go do 3 examples, but we're only going to do 1 per day because since they're multi-part problems, they take a little bit of time. So today, let's look at example 1. So you start just by reading this problem. A 0.750 kilogram beanbag is dropped from 3.5 meters. When it hits the ground, it only takes 0.20 seconds for the ground to stop it moving, and we have to determine the average normal force the ground exerts on the beanbag. So I'm going to need to summarize this problem, and that'll help me. So when I'm thinking about this problem, I notice that a beanbag is being dropped, and then the ground stops the beanbag. And this and then provides us our natural separation. It's because the situation of the beanbag being dropped, the beanbag is falling, it's being affected by gravity, is different from the ground stopping the beanbag. The beanbag is in contact with the ground and there's gravity pulling it down and the normal force from the ground. The free body diagrams for these two situations are different, and that's why we need to separate them. Now I'm going to go ahead and I'm just going to highlight my variables to determine what I need to use. The 0.75 kilograms is usable both when the beanbag is being dropped and when the ground stops the beanbag. And I'm going to color code my highlighting here. The 3.5 meter high drop is a situation that happens when it's being dropped, and the 0.20 seconds is how long the ground takes to stop it. The last thing that we have here is we have to determine the average normal force the ground exerts. Now this begins looking like a force problem, so I'm going to make a free body diagram trying to find my normal force as the ground is stopping the beanbag. So this beanbag is contacting the ground, there's a normal force, but gravity is also pulling it. I'm going to go ahead and I'm going to say that up is positive and I'm going to say that down is negative for any amount of adding or subtracting I have to do. And the net force equation in this case should be pretty easy for us to make. It's going to be the normal force subtracted by the gravity. Now don't make this mistake of saying that the normal force is equal to the gravity. The beanbag is accelerating, and if the beanbag is accelerating, they cannot be balanced forces. Just looking at this, I actually already know how to find my force of gravity because I can take the mass multiplied by 9.8. 7.35 newtons. Now that's a start. Let's try to break down our net force equation into its formulas or variables that we know to help us. The net force is mass times acceleration. The normal force has no formula, but that's the thing that we're trying to solve for. And the gravity, we actually already know, is 7.35 newtons. The mass is actually something we already know as well. So I should rewrite this whole formula like this: 0.75 times A multiplied by the equals the normal force minus 7.35. Now we want to find the normal force, but it looks like my acceleration is my unknown still. So if I find a way to determine my acceleration, that will help me solve for this problem. Now the only other thing that isn't force that uses acceleration is kinematics. So I'm going to see what kinematics things I know, and will that help me find my acceleration. The beanbag comes to a stop, so that means the final velocity is 0. The time it takes is 0.20 seconds. And that's all we know. Some people might say, Mr. Westergaard, the beanbag was dropped. That means an initial velocity is 0. But watch out, that dropped initial velocity occurs when the beanbag is being dropped. It is not after my and then separation. That's before my and then separation. Now this seems like an unsolvable situation. I don't have enough information, but this initial velocity here is the velocity of the beanbag at the moment it hits the ground. And the velocity of the beanbag, the moment it hits the ground, might be the initial velocity of the ground stopping the beanbag, but it's the final velocity of the beanbag falling through the air. So if I find the final velocity in my beanbag is dropped situation, then that'll actually give me the initial velocity of my ground stops the beanbag situation. So I can use that to help me. This beanbag is being dropped. We want to know the final velocity. We know gravity is accelerating it, and we know that it drops 3.5 meters. I can go ahead and use my Vf squared equals Vi squared plus 2AD formula to solve for this equation. Remember, when you're taking the square root of something, you can choose the positive or the negative solution, whichever makes the most sense for your problem. So Vf is equal to 8.28 meters per second. And hopefully you also identify that it should be going negative since this beanbag is going downward. So this can become the initial velocity here, 8.28 meters per second in the negative direction. Well, that means we have all the things that we need to find the acceleration, because acceleration follows the formula of Vf minus Vi all divided by t. And we see our acceleration is positive 41.4 meters per second squared. And this can now be substituted into my net force equation, and that will allow me to solve for the normal force. And since that is subtracting 7.35, we can add 7.35 to both sides. And we find out that our normal force is 38.4 newtons. And hopefully it makes sense that the normal force is larger than gravity because it has to accelerate the beanbag to a stop. So that's all what we're going to do for today. Check in tomorrow to see the next example. Have a good day.